Good morning, everyone. Welcome to our Day 2 section for this year's IWAM. And today we're going to begin with our graduate student talks. And our first speaker is Maram, and it seems like she's very well known here. So I'll just be short. And her title for today is Molecular Layer Deposition of AlF-MOF thin film for Selective CO2 capture, and she's now currently in Canada. Okay, let's welcome Maram.
Hi, good morning. It's good to see familiar faces. Thank you for coming very early. A little bit about myself. I grew up in Ruwais City, which has the 4th largest single-site oil refinery in the world. And don't get me wrong, I love carbon dioxide. It's a childhood memory, but it's causing a lot of trouble around the world. We've seen the wildfire, ice melting, and the death of thousands of species. And these aren't just numbers and facts. These are a call for action. We know MOFs are one of the best materials at capturing carbon dioxide, sometimes selectively, like this MOF right there. It's aluminum formate MOF. It was published in 2022 by your group, sir. It was proven to be like, it can capture carbon dioxide selectively throughout a size-selective adsorption, and it also can form hydrogen bond with carbon dioxide once it's in the pores. The second I saw this MOF published, I went crazy because, I mean, look at the building blocks. Formic acid, it can't get smaller than that. I came from an ALD lab. I know this is a jargon. I'm going to let you know what that in a second. Atomic layer deposition. We love volatile compounds because we can translate materials into microelectronics devices throughout making a thin film out of it. That's why. So we wanted to see if we can translate this MOF structure into a ultra-thin film and integrate it into microelectronic devices. And the way we know that we got this MOF on the surface, the right structure we're looking for, is if it was a crystalline on the surface, and if it was going to return the selective adsorption of carbon dioxide. So that's what we wanted to test here. Atomic layer deposition. This is just a brief overview. If you have this is one of the most famous recipes in ALD. If you make a thin film, an atomic layer at a time. So if you have this system of trimethyl aluminum and water, and you have an hydroxylated silicon wafer surface, you bring in the TMA under vacuum in a small dosage, and TMA will react with every last oxygen on the surface, if it's the right amount of dosage. And then any excess of trimethyl aluminum on the surface get purged outside the system. It does not get accumulating on the surface. So it produces one single layer of aluminum on the surface. If you bring in the second precursor, that's the water, it's going to react with the aluminum on the surface. It does not accumulate, one layer thick. Everything extra get purged outside the system. So we wanted to adopt this methodology, but by exchanging water with like just formic acid. So this is what we did here. Now this kind of materials are already known. It's called metal cones. It's the hybrid inorganic organic materials is synthesized by MLD. Oops, what's going on? OK, sorry for that. It's synthesized by MLD, and it's known to be non-porous and non-crystalline. So what we wanted to do is to deposit this MOF. It's going to be alicone as deposited, non-porous, and see if we can crystallize it on the surface. And in MLD, molecular layer deposition, in order to know how much material you should deliver to the surface, so it's not too little, it's not too much, you have to generate what's called the saturation curves, which are the two curves you see here. At the y-axis, you see in the growth per cycle, that's the thickness per cycle, and here is the dosage of the precursor. In this recipe, you have two precursors, formic acid and TMA. For every saturation curves, you have to set one of the precursors is stable, the pulsing is stable, and then you have to vary the concentration of the other precursors. What you want to see here is a plateau in the thickness, because no matter how much you increase the dose, that should never increase the thickness even further, because we're talking about an atomic layer at time, right? The way we measure the thickness here is by atomic force microscope, at which we deposit the thin film, that is this thing here. We deposit it, and then we scratch the surface. And then we, with a needle, in the atomic force microscope, it goes across that scratch, and you get from the imaging process, you can see the height distribution at the silicon side and the height distribution at the thin film side. And the distance between those two tells you what the thickness of the film is. So we're using this in order to generate the saturation curves. We also monitored the growth by quartz crystal microbalance. It's a normal balance, like the one you use at home, except this one can measure atoms. So we throw one of these in the chamber, and we were looking at the growth. So on the y-axis, you have the mass gain, and every time you pulse a material on the surface, you can see as an increase in the mass on the balance. And then you want to see a stepwise growth, and that's how you know it's an MLD system. So, and then the as-deposited film, we try to see if it's crystalline. You see this line here. It's not a line I draw. It's just the XRD. It's just very flat. It was not crystalline as deposited. And we thought it's maybe the signal. It's not very intense. But so we tried to deposit it on glass fiber to increase the surface area and makes it easier to handle as a thin film. And it was not crystalline. So we placed it in a sealing tube with a 1 drop of formic acid. That's the same linker we used. And then seal it, heat it at 55 degrees Celsius for 2 days. And the silicon wafer, you can see a color change from blue to purple. Glass fiber doesn't have any color change. However, if you look at it by SEM, this is the glass fiber without depositing anything on it. This is the as-deposited thin film. You gotta trust me, there's something here. It's just super conformal. And then here is after it got crystallized. And look at this beautiful crystals on the surface. And it's very conformal, like it's taking the shape of the glass fiber. XRD compared to the bulk, it's very comparable. Those extra aluminum peaks are coming from the holder at which we did the analysis. So we crystallized it. Yay. Now, the cherry on the top is if it can absorb carbon dioxide selectively. So this graph over here comparing the as-deposited MOF. You can see this is a carbon dioxide absorption, no absorption whatsoever. And then if you compare it to the bulk right there, you can see it's a very comparable trace. And the second you start introducing carbon dioxide, you see uptake. And then try to take it away. Doesn't want to give it back. Okay, so, and we know this MOF doesn't like nitrogen. So you try to do a nitrogen absorption here versus the carbon dioxide. Nitrogen is a trace amount, and then carbon dioxide is very high and as expected at 4 millimole per gram. I call that a success. I don't know what you call it. I want to take a second to thank my group, the Berry Lab, the Gonya group at Western University, Parsons group at NC State University. Those are our collaborators and all our funding agencies. And a special thank to Sophia. I don't know if she's here, but she's the one who funded the trip here, and she supported me throughout coming here. Thank you very much for your attention and questions.